Hey everyone, I'm Nick, and this is C++ from scratch. So in this episode of the series, we're going to be talking about the basics of std move and move semantics. So in previous videos, we've talked about how we sometimes want to prevent copies inside of our programs. And this might be for functional reasons, like the case with std unique pointer that can't be copied, or it might be for performance reasons. So say we have a very large vector that would be expensive to copy. Now, one of the ways that we have around copying in C++ is this idea of moving and move semantics, where instead of copying some resource to, say, a new object or a different object, we can steal the underlying resources. So that's what we're going to be looking at today with some simple examples. So let's go ahead and get started and create a new file called move.cpp. And inside of here, we're going to include IO streams so we can do some printing. And we'll also include memory, right? So we can play around with our std unique pointer here. Then, of course, we'll need a main function, core of our C++ programs. So let's go ahead and start off by just creating a unique pointer that is going to manage some dynamically allocated array of integers. So we can create some pointer1 and set this equal to std make unique. Let's go to manage an array of integers, and let's just say 10 integers here. Right, so we've created a unique pointer. Now, something that we can't do with our unique pointer, as we kind of mentioned earlier, is we cannot copy it. So I can't do something like auto pointer2 is equal to pointer1, right? I can't use the copy constructor of my unique pointer because it simply doesn't exist. So if I go ahead and try to save this and compile move.cpp, we can see that my compiler yells at me a bit. It says error, use of a deleted function. And specifically that deleted function was the copy constructor of our unique pointer. Now, even though we cannot copy, say, a unique pointer, there are still cases where we might want to give up the resources that our unique pointer is managing and shift it over to, say, a new unique pointer, right? Our unique pointer may be coming from somewhere else, and we want to move that contents, right, or that underlying memory that it's managing to, say, a new unique pointer. And the way that we do this in C++ is through this idea of moving and move semantics. So if we go ahead and look at the CPP reference page for std unique pointer here, we can see that our unique pointer class satisfies the requirements of move constructible and move assignable. So we can move our unique pointer, but we can't copy it. So it doesn't satisfy copy constructible or copy assignable. But what exactly do we mean by this move constructible? So I think that the best way to kind of discuss that is by looking at the CPP reference page for move constructors. So move constructors look very similar to our copy constructors, right? They have some class name or struct name, right, as the name of the method. And then they take something of type of whatever class it is. But instead of by reference here, it takes it by this R value reference that we haven't seen before. So this double ampersand sign. So we'll talk about that in just a little bit. But let's go ahead and look at the explanation for how these move constructors work. So the idea behind move constructors is that they steal the resources held by the argument, right? So we're creating a new object based on some other object, but instead of copying the resources, so say copying some memory, what we're going to do is steal that memory away from what currently has it. So in the case of, our unique pointer here, right? Pointer1 is managing this array of 10 integers, right? If we're going to move it, right, using move construction to pointer2, right, pointer1 would no longer have this array of 10 integers here. It's going to be stolen away and given to pointer2. Right? But this doesn't just apply to, say, dynamically allocated memory. It could be some other resource like a TCP socket, IO streams, or even running threads, right? But the idea here is that we're stealing away resources from one object and giving it to another instead of making a copy of them, right? Now, one of the things when we do a move is that it says specifically it leaves our argument, right? So whatever we're doing a move from in a valid but otherwise indeterminate state, right? Now, what does that really mean in practice? Now, all that really means is that, we're still able to use, say, our pointer1 here, but we shouldn't use the value that pointer1 used to have before we did a move here. So we shouldn't rely on this underlying pointer still being valid here. And some of our STL containers right, have, say, a fully specified state after doing something like a move, but other containers don't. So something like a stood string or a stood vector may be empty after we do a move, after we steal away those underlying resources, but they may not. So it's not something that we should rely upon. So we can still use the container, but we shouldn't rely on the value, right, being what it was before the move. However, there are containers and objects, so things like stood unique pointer that we're working with, that do have a fully specified move from state. So after we move and move the underlying resource from a unique pointer, the state of our unique pointer is fully specified and we can rely on that. And we'll look at that in just a little bit. But before we get into that, we have to talk about, how exactly do we use this move constructor, right? All we have so far is, we're trying to use our copy constructor here, but how do I tell our compiler that we want to use a move constructor? And that requires us to talk a little bit about these value categories and L values and R values. So we have these 5 major value categories in C++ that describes the values inside of our programs. Now we're going to keep things at a pretty high level here and not really deep dive into what a GL value is, a PR value, an X value, etc., etc. We're going to mainly focus on L values and R values, because I think these can be fairly intuitive, right, at least at a very high level. So as it says here on CPP reference, L values are historically called L values because they are they were typically on the left-hand side of some assignment expression. So there are some, say, named thing, so something like this pointer1 or pointer2 variable, they have an address and they can be assigned to, right? Now on the other side of things, we have things like R values, right, which are typically on the right-hand side of these assignment expressions, and say they don't have names, right? So they might be some nameless temporary, or they might be some immediate value, some integer like 8. And these are things that we typically do not assign to, right? So, for example, here pointer1 and pointer2 are going to be considered L values here. And stood make unique, right? This return value from this called a stood make unique, that would be an R value over here, or we'd consider in that class of things. Now, one of the main differences that we have between L values and R values is how we treat them in terms of copying and moving. So by default, with our L values, right, we can have references to these things, but we typically copy them, right? We don't move them. But things like these nameless temporaries and like return values are things that we do move. So we do move things like R values. Now we have a bit of a special case here with things like, some of our L values. So some of our L values we can convert to be types of R values or R value references that we can move. And the way that we do that is through something like stood move here, right? So stood move, you can see, as it says in the description, stood move is used to indicate that an object T may be moved from to allow the efficient transfer of resources from one object to another. So it's a way that we can tell our compiler, hey, you are allowed to move this, even though it's not a type of value that you're typically allowed to move, provided that, it has specified something like a move constructor, right? So it says how it can actually be moved. So let's go ahead and see how we can do that with our unique pointer here. So what we can do is we can include utility, right? That's where this stood move is defined. So we'll go ahead and include utility. And then instead of just doing this assignment here, we'll change the value category for this pointer1 here by using this stood move on pointer1. Now again, stood move isn't forcing, right, our compiler to move pointer1. What it's doing is saying you're allowed to move this. So in this case, what we'll see is that we're no longer going to get a compiler error anymore. Our compiler is going to move pointer1 and do this move construction of pointer2. So it's going to steal away this underlying resource. And we can actually see that, right, stood unique pointer, as it mentioned inside of our move constructors page from CPP reference, has a fully specified state that we can rely on after moving. So one thing we can do is we can just print out the underlying pointer, right, for our unique pointers here. So we can do something like stood cout, and we can print out, pointer1 before move, and we'll go ahead and print out pointer1.get, right? So we'll use a get method down here of our unique pointer to get the pointer to the managed object, this dynamically allocated array of integers, followed by a new line character. Then we'll go ahead and print this again after we do the move. So we'll see what the state pointer 2 is in after the move. So let's go ahead and change this to pointer 1 after move. And then let's go ahead and look at pointer 2, right, after we've done this move, right, and see what the underlying pointer is for our new unique pointer here. So let's go ahead and change this to pointer 2, save everything, and let's go ahead and compile move.cpp and call our output executable just something like move. And then we can go ahead and run this. And what we end up seeing is that pointer 1 before a move, right, it has some pointer to some dynamically allocated array of memory that we got from make shared. But after we do the move, we see that the pointer is nulled out. It's 0 now. That underlying resource was stolen away, right? And it was given to pointer 2. So you can see that pointer 2, the pointer that it's managing after we do this move, is the same one that pointer 1 used to have. So pointer 2 just stole the underlying resource of pointer 1, right, through that move construction here. So moving is just a way that we can transfer resources from, say, one object to another instead of copying them. And there are a number of places where we might want to do that. So for example, in a loop, we may be calling some function to get some result or set some object, right? But we don't want to copy that result into, say, something like a vector, right? So maybe we're constantly adding things to a vector. So we get something from a function, then we add it to a vector. Instead of just, copying that value into our vector over and over and over, we could move that value into our vector, right? And just steal those underlying resources. So that's one of the things that we could do and why moves are important. Okay, so there's a lot to take in here, and this is just a brief introduction to this idea of moving and move semantics and how we use std move. So again, we use std move to just tell our compiler, hey, you're allowed to move something. And this works great with, say, our STL containers like std vector or std string, or even things like std unique pointer, right? And we can also specify things like these move constructors for our classes. Now that's going to go ahead and do it for today. I'll put all of these links below the video to these different CPP reference pages. And of course, you can find out more about, or you can find out more of these examples and play around with them at github.com/coffeebeforearch. But that's going to go ahead and do it for today. As always, I'm Nick, and I hope you have a nice day.